Hello everyone, welcome to another video of Hamilton mechanics. In today's video, we'll be talking about the Poisson bracket. So let's begin. So in our last videos on the Hamilton equations, we talked about the Hamilton equations, and we derived these two equations of motion for the position and for the momentum of some particle. But we know that there are other quantities in physics besides momentum and position. So we have some other quantity called big Q, which is also a function of position and momentum. Is there going to be some sort of analog to the Hamilton equations for the equations of motion for big Q? It turns out that there is, and we use the Poisson bracket to do that. So to calculate d of big Q over dt, we can just use the multivariable chain rule. So that's going to be dq over d small q over dt plus d big Q over dp and then dp over dt. And these quantities are familiar to us because they show up in the Hamilton equations right over here. So we can just plug those in to get that d big Q over dt equals dq over dt partial h over partial p minus dq over dp and then partial h over partial q. And this should be a q over here. And these should be partial derivatives, technically speaking, by the way. So we get this big expression over here for the equations of motion for q. And we can actually define this as being some bracket of q and h. We call this bracket the Poisson bracket. So this Poisson bracket of the variables q and h look very similar like the commutator. Because recall that the commutator of q and h is going to be qh minus hq. And the Poisson bracket is kind of like that, but instead of having just q and h being multiplied together, we have the derivatives of those functions with respect to those variables kind of like being multiplied together. Because here we have q and p minus p and q, so that's sort of the motivation of defining something called the Poisson bracket that looks kind of like the commutator. So, and we call this new formula where dq over dt equals the Poisson bracket between q and h. We call this the Hamilton general equation of motion. And to be specific, the Poisson bracket between two variables, a and b, is going to be defined as partial a over partial q, partial b over partial p, minus partial a over partial p, partial b over partial q. So that's how we are going to define it for the general case. Now it turns out that we don't have to take the Poisson bracket between some variable and the Hamiltonian. We can choose the Poisson bracket of some variable and say the momentum instead of the Hamiltonian. Well, what does that look like? Well, that's going to give us, using this general formula, partial q over partial q, partial p over partial p, minus partial q over partial p over partial q. Well, p and q in Hamiltonian mechanics are taken as independent variables, right? So that means that this is going to go to 0. And partial p over partial p is just 1. So this tells us that the Poisson bracket between big Q, and p is going to be partial q over partial small q. This is really interesting because the Poisson bracket between some general quantity q and the Hamiltonian give us the time derivative of q. But the Poisson bracket between some general quantity and the momentum gives us the rate of change of q over the position instead of time. So this makes us say that the momentum, p, it generates spatial translations. because when we take the Poisson bracket between Q and P, we get a rate of change of the spatial coordinate Q. And likewise, we say that the Hamiltonian, it generates time translations, because when you take the Poisson bracket between Q and the Hamiltonian, we get the rate of change of Q over time. Likewise, we can actually look at the Poisson bracket between big Q and then small q as well. That's going to give us, and this is going to be 1, right? This is going to be 0. So this gives us minus partial q over partial p. So this is telling us that when we take the Poisson bracket of some general quantity big Q with the spatial quantity small q, we get out the negative rate of change of some quantity over the momentum. So it's like position generates momentum translations. So basically the summary of this video is that there is some useful operation called the Poisson bracket. And the Poisson bracket of some general quantity with the Hamiltonian is going to give us the time translation, or the rate of change of that quantity over time. And then when we take the Poisson bracket of some quantity with the momentum, that tells us how it changes over space. And when we take it with the position, it tells us how it changes over the momentum, if that makes sense. And we can also go further and prove that the Poisson bracket of A and B is going to equal minus the Poisson bracket of B and A. And there is an analog to the Poisson bracket in quantum mechanics called the commutator, where the commutator of two quantities A and B is just AB minus BA. In fact, just like how the commutator, or the Poisson bracket of Q and H, gives us the derivative of Q over T, the commutator of Q and H, scaled by some factors, is going to give us the rate of change of some operator quantity over time in quantum mechanics, where Q and H are also operators. And we call this Ehrenfest's theorem. So there are many analogs of Hamiltonian mechanics to quantum mechanics, and we'll be exploring more in the future. So thanks for watching and have a great day. Bye.